This is the second lesson of a topic titled Real Zeros of Polynomial Functions. Lesson 4b is focused on finding rational zeros. We'll learn about the Rational Zeros Theorem and how it offers possible zeros for a polynomial function. We'll find the real zeros of a quintic function and the real zeros of a quartic function. I'm Mr. Stark, and this is Polynomial and Rational Functions. Let's keep dividing synthetically. The first thing we need to cover is the Rational Zeros Theorem. Remember how the standard form of a polynomial function starts with a sub n x to the n? And remember how it ends with a sub 0 x to the 0, the y-intercept? Well, the Rational Zeros Theorem uses a sub 0 and a sub n. First, it says let p be a factor of a sub 0 and q be a factor of a sub n. So if a sub 0 is 6, p can be positive or negative 1, 2, 3, or 6. If a sub 0 is 36, like the example we're about to do, p can be a lot of numbers. The second thing that the Rational Zeros Theorem says is that p divided by q is a possible zero of a polynomial function. That means we divide the factors of a sub 0 by the factors of a sub n to get the possible zeros of the polynomial function. So let's try it out for this quintic function, f of x. The possible zeros are rational, so I'll write a fraction. The factors of 36 are positive or negative 1, 2, 3, 4, 6, 9, 12, 18, and 36. And the possible zeros of a sub n, which is 2, are positive and negative 1 and 2. There are a lot of possible zeros. Notice that 1/2 is a possible zero, 1 divided by 2. 3/2 is a possible zero, 3 divided by 2. 6/2 is a possible zero, but that's 3, which is already taken care of by 3 divided by 1. 9/2 is a possible zero, 9 divided by 2. And I think that covers it. So those are all of the possible rational zeros of this function. There can also be irrational zeros and imaginary zeros. The next thing we'll do is graph this function and get a hint from it, because doing synthetic division with all of these zeros would take a lot of time and paper. Notice that this graph has a positive n behavior in the future because the leading coefficient is positive. Also, the degree of this polynomial is 5, so I'm expecting there to be 5 solutions. If they're real, they'll cross the x-axis. If they're not real, we won't see them. I see 3 possible x values that make this function equal to 0. Negative 3/2, positive 3/2, and 2. Since the possible rational zeros are as low as negative 36 and as high as positive 36, I'll change my window so I could see those x values. Oh well, there are no more real zeros or x-intercepts that I can see, so maybe there are 2 imaginary zeros. Now we're ready to do synthetic division. I usually like to start with the whole numbers. So we'll put 2 in the box and the coefficients to the right. We'll draw a horizontal line and drop down the 2. Here we go. 2 times 2 is 4. Negative 1 plus 4 is 3. 3 times 2 is 6. Negative 2 plus 6 is 4. 4 times 2 is 8. Negative 14 plus 8 is negative 6. Negative 6 times 2 is negative 12. Negative 6 plus negative 12, negative 18. And finally, negative 18 times 2, negative 36. And we get 0 as the remainder. At this point, we could write the new polynomial, but instead, we'll continue dividing with those numbers that are already there. Let's do negative 3/2 first. You'll see why later. Negative 3/2 goes in the box, and we drop down the 2. Draw a horizontal line. Here we go again. 2 times negative 3/2 is negative 3. 3 plus negative 3 is 0. We like this one. 0 times negative 3/2 is 0. 4 plus 0 is 4. 4 times negative 3 halves is, well, 4 divided by 2 is 2, times negative 3 is negative 6. Negative 6 plus negative 6, negative 12. Negative 12 times negative 3 halves, well, negative 12 divided by 2, negative 6 times negative 3 is 18. All right, negative 18 plus 18 is 0. We love it when that happens. That means negative 3 halves is a real 0 of this polynomial. Let's look at the graph one more time. You might have noticed this before, but at x equals 3 halves, it doesn't actually look like that's a 0. It's slightly off. But let's prove it algebraically, or analytically. The positive 3 halves goes in the box now. Drop down the 2, draw the line. 2 times 3 halves is 3. 0 plus 3 is 3. But things start to get a little dicey here. 3 times 3 halves is 9 halves. 4 plus 9 halves, well, 4 is 8 halves, plus 9 halves is 17 halves. I don't think this is going to work, because 17 halves times 3 halves is definitely not 12. So let's erase that work and write the polynomial that we ended with. Remember that the 0 was the remainder, so negative 12 is the coefficient of x to the 0, 4 is the coefficient of x to the 1, 0 is the coefficient of x squared, and 2 is the coefficient of x cubed. If this was a quadratic function, we could use the quadratic formula to find the last two zeros. But since there's no cubic formula, we can't find that last 0 that we saw in the graph. So it's likely irrational. That's where our work ends for this example. The real zeros are x equals 2 and x equals negative 3 halves. In this example, we'll repeat the same process, but we'll end with a quadratic function, so we'll be able to solve it all the way. Let's find the possible rational zeros first. Notice that a sub 0 is 8, and the factors of 8 are plus or minus 1, 2, 4, and 8. Notice that a sub n is 2, and the factors of 2 are plus or minus 1 and 2. Since there are not many possible rational zeros, we don't really need the calculator, but we'll use it as a tool anyways. Since this polynomial has an even degree, 4, the n behaviors are the same. And notice there are 4 real zeros, 4 x-intercepts. Let's see. It looks like negative 3 halves is a 0, negative 1 half, 3 halves, and 4. Let's do some synthetic division again. Let's start with 4 and put the coefficients to the right, draw a horizontal line, and drop down the 2. Here we go. Follow along. 2 times 4 is 8. Add to get 1. 1 times 4 is 4. Add to get negative 4. Negative 4 times 4, negative 16. Add to get negative 2. And negative 2 times 4 is negative 8. Remainder of 0. Thus, 4 is a real 0. Let's do negative 1 half next. Sometimes when numbers come in pairs, they're actually irrational, not rational. Let's put negative 1 half in the box, draw a horizontal line, and drop down the 2. And here we go. 2 times negative 1 half is negative 1. Add to get 0. 0 times negative 1 half is 0. Add to get negative 4. Negative 4 times negative 1 half is 2. We get a remainder of 0 again. Thus, negative 1 half is a real 0 of this function. At this point, we could do synthetic division with positive and negative 3 halves. But it's actually easier to solve the quadratic function we're left with. Notice that negative 4 is the x to the 0 coefficient, 0 is a coefficient of x to the 1, and 2 is a coefficient of x squared. So the quadratic function is 2x squared minus 4. We're trying to find zeros, so let's set that equal to 0, and then add 4 to both sides. So we have 2x squared equals 4. Divide by 2 to get x squared equals 2. Then take the square root of both sides, and we get x equals positive and negative square root of 2. We could have used the quadratic formula to solve this equation, but the coefficient of x to the 1 was 0, so it allowed us to use the square root property. The square root of 2 is approximately 1.41. And that's pretty close to 1.5. But I should have never written 3/2 or -3/2 because those were not possible rational zeros. Let's make some conclusions now. There were 4 real zeros, -1/2, 4, square root of 2, and negative square root of 2. -1/2 and 4 are rational. Positive and negative square root of 2 are irrational. Remember, there can also be imaginary zeros, and we'll cover that in the next lesson. And that's the end of topic 4 of the polynomial and rational functions unit. I'm Mr. Stark. Join me for the next lesson, lesson 5. Did you press that subscribe button yet? Give me a thumbs up if you liked the video. If you have a question, you might as well ask it. Do you have a comment? Feel free to add it. Hey, thanks for watching.